Okay, welcome back everyone to our third and last invited talk by Reid Barton about geometric homotopy theory via simplicial sets.
All right, thanks, Felix, and thanks to the organizers for inviting me. This is, I'm very happy to tell you about a project that has been on the back of my mind for a long time, but recently I was able to put some pieces together and kind of get this thing moving a little bit. And so my talk has a kind of subtitle, which is how not to do synthetic homotopy theory. I wanted to start with this quote from the hot book. So this is from back in 2013 when the homotopy type theory was just being born. It's about how in Univalent foundations, there's this synthetic approach to homotopy type theory, in which homotopy types are the basic objects, rather than being constructed using topological spaces or some other kind of set theoretic model that's more primitive. And I would say that, if we look back at the last 12 years since the book was published, this synthetic homotopy theory approach has been extremely productive and fruitful in terms of producing either like new perspectives on previously understood constructions, or maybe just cleaner proofs in general of stuff that has been done in the past in a more traditional style. On the other hand, homotopy type theory is, after all, a flavor of type theory. And in type theory, it's supposed to be a foundation where I can do any kind of mathematics that I like. And that includes homotopy theory. So another approach that we could take is inside homotopy type theory, we could just try to recapitulate, as it were, sort of all standard homotopy theory done with simplicial sets or topological spaces and so on. And there might be some kind of issues if we really want to stick to constructive reasoning, which I do for this talk. But maybe this only requires some kind of minor adjustments. Now, why would I want to go to all the trouble of doing that? Sounds like a lot of work. Well, the main reason that I can think of is maybe I have something I don't know yet how to do synthetically, or I don't know whether it's possible to do it synthetically. And for me, the natural examples of those things would be some objects that arise from geometry, like topological K-theory or complex coboards of the spectrum. And I'm going to use topological K-theory as my kind of motivating example. This talk is not about K-theory, so it's totally fine if you don't know anything about it. But the point is, it's something that we know how to do classically. We don't know how to do it in synthetic homotopy type theory. And so, well, maybe it's something we'd like to have. So why might we want to have it? Here's a very famous theorem from the classical days of algebraic topology. It's called the, Hopf invariant one, I meant to put down on the slide. It tells us which spheres emit something called an H-space structure, which is just a binary operation that has a unit. And the theorem says that, well, the n-1 sphere has an H-space structure if and only if, in the end, the dimension, or n, is 1, 2, 4, or 8. And this theorem has a very slick, it's literally less than a page-long proof. Once you have the machinery of topological K-theory and you know something about something called the Adams operations on it, which I'm definitely not going to talk about today. But one thing I want to note about this theorem statement is it doesn't involve this topological K-theory in the statement, right? It's just an ordinary statement about ordinary synthetic spheres, and it's extremely easy. I mean, I guess it's easier enough to write it down in the statement in book hot, and so it would be sort of fair to ask for a proof also in book hot. And to be clear, I don't know how to do this, but it's something that I would like to be able to do. And that's why, one possible approach to building topological K-theory could be, well, I work on some kind of cohesive setting, which is specifically designed to talk about geometric objects like Lie groups and so on. But I don't really want to do that because I'd rather ideally just prove a theorem in book hot by just building K-theory in book hot. And I'm willing to do a lot of work to get that if it's possible. Okay, so that's sort of the premise of this project. And so if we don't have any synthetic way to try to build K-theory, we might just try to do it what I was describing as the traditional way. So first, by some kind of traditional construction, I'm going to build a simplicial set, say that I'll just call Z cross BU. And then I want to build somehow also this bot map. And this is part of this is outside the scope of this talk. And then the second step is, well, these are simplicial sets and a map of simplicial sets. And I want to take somehow a shape of it and get the actual homotopy type of those simplicial sets. And that's the thing that should be the underlying types that appear in the K-theory spectrum, ideally. And this second part of sort of taking the homotopy type as simplicial set is what this talk is really supposed to be about. Okay, so what's the problem here? We would need a way to take some kind of simplicial set, or really like any combinatorial model of homotopy theory whatsoever, and turn it into one of these synthetic homotopy types. So for example, if I took the n simplex, that's like a combinatorial structure, and I take its boundary, then that's supposed to have a shape, which is the n-1 sphere, but like as a synthetic sphere that we build by higher inductive types, iterated pushouts or suspensions. And we'd like some general process that can take in a simplicial set and output this synthetic sphere. Not to produce spheres, which we already know how to produce, but to produce these other objects like topological K-theory. And unfortunately, we don't know at the moment whether this is possible in book homotopy type theory or not, or even in cubical hot. The problem is, well, if you try to do it in a kind of direct way, you find that you really want to write down like some infinite amount of coherence data, and type theorists usually get very angry if you try to write down infinite definitions. But there are many extensions of homotopy type theory that that would make this sort of realization problem solvable. It's really a reasonable thing to ask for. So for example, if I have some kind of extension of homotopy type theory in which I can talk about simplicial types, then I have a construction of the shape, presumably. I mean, assuming my theory is sort of good enough, I take my simplicial set. A set is just a zero truncated type, and so then I can just regard it as a simplicial type, presumably. And then the shape thing that I want to define is the colimit of that diagram. And that's the correct construction. We would need simplicial types, either as a sort of direct feature or as part of a general theory of infinity categories. It's a pre-sheaf infinity category. So we don't know how to do this in book hop, but it's reasonable to expect that in some extension of hop we can do it. And for the moment, let me just assume that this problem has been solved somehow. So I have some construction that takes a simplicial set, like the boundary of a simplex, and can output the shape that it's supposed to represent, like the synthetic sphere. So there's actually a kind of second problem, which I don't know if this is a really good illustration of, but if we go back to my plan to build K-theory, there was this map of simplicial sets from something called Z cross BU to something to, well, it's double loop space. But that double loop space is like the simplicial model of double loop space. It's built by like maps of a simplicial sphere into this complex or something like that. And if I take its shape, I'm going to get a map from the shape of the thing on the left to the shape of the thing on the right, like ideally. But what I wanted to build a spectrum was something slightly different, which is a map from the shape of the thing on the left to not the shapes of some simplicial double loop space, but rather the actual synthetic double loop space of the shape of the thing. And so it's not really enough to just have a construction that turns a simplicial set into a shape. You also need to be able to control it somehow and to understand, for example, if I take the shape of the simplicial loop space of something, is it going to be the same as loops on the shape of the thing that I started with? Okay, so these are sort of the two problems that I'd like to try to attack in the talk today. And more broadly, the question would be, if I have some push out square or pullback square of simplicial sets, when can I know that the shape operation is sending it to a push out or pullback square of types? So yeah, so the overview of this talk is, I don't know how to do this in book hop, like I've been saying, but what I do know how to do is add just a sort of relatively small number of axioms that are about two things. One is the subuniverse of shapes, this word that I keep using. And the other one is that I need some kind of interval type, which is going to help me build things that I can take the shape of. And using these axioms, I'm going to try to address the questions on the previous two slides. And a quick layout of the talk is, well, first of all, I just want to step back and kind of give another big picture of what's going on, because there's a lot of stuff that gets involved in this. Then I want to describe what the axioms are. They're very complicated. Then I want to give a quick overview of how to do basically simplicial homotopy theory in this setting. And then at the end, very quickly, I'm going to talk about the way to connect this to geometry. How do I actually build like a model for the thought map or something like that? Okay, and I definitely have not actually succeeded in constructing topological K-theory. That's going to require a lot of other ingredients that I have not really thought about yet. All right, so let me talk about the general approach a little bit. So it's important to understand, because some parts of what I'm going to do will look a lot like what you do when you try to build a model of homotopy type theory in your meta theory. This whole construction, this whole development is going to take place inside like ordinary homotopy type theory plus like some number of axioms. And we're going to try to work as much as possible with sets. And when I say set, I just mean an H set. So like a zero truncated type. I never mean like, well, in some models, when I talk about models, I mean an external set. But when I'm talking about this development, I mean like a zero type. And well, since we're doing the mathematics of the zero types, we kind of already know a lot about the mathematics of zero types. It's just called sort of constructive mathematics that's sort of set-based. And I'm not going to hold back from using any theorem that I know how to prove in that context. So for example, simplicial sets. I know how to write down the definition of a simplicial set. There's no coherence problems involved in that because everything is set level. And I also know how to build a model structure, a colon model structure on the category of simplicial sets. And recently, well, somewhat recently now, so Simon Henry and then gave a construction of this colon model structure, which is constructive. And this was also, I think, simplified and sort of streamlined by these authors, Gambino, Sadler, and Shumuel, a few years ago. And we're going to maybe not use this entire model structure, but it provides a kind of useful framework for understanding what's going on here. And that might be, so this might be something that you're used to thinking of as like something that happens in the meta theory to produce a model hot, but I really want to emphasize that that's not my plan. My plan is to take the whole, I guess, 50 pages or so of this GSS 22 paper and then write them all down inside Homotopy type theory. And then inside Homotopy type theory, I have a model structure, whatever exactly that is, on the category of simplicial sets, which also live internally to my development in Homotopy type theory. And then at the end, I need to also, I'm going to explain how to extract one of these simplicial sets from some geometric object. And just to give you some rough sense of scale, I haven't thought about this very carefully. Maybe I need another like 100 pages of general theory on doing some kind of constructive geometry just to turn my unitary group or whatever I'm interested in into a concomplex that I want. And so this is, I think, a little bit unusual for Homotopy type theory developments. Usually they're kind of much smaller scale in terms of like the size of the mathematics that gets put into Homotopy type theory. But since we have all of this stuff done already, my purpose is to sort of redo traditional homotopy theory in this setting. I might as well take all these facts that I know and just put them into my object theory. What am I gaining by doing all that work? Well, normally, if I think about model categories and simplicial sets and infinity categories and so on, there's sort of this perspective that there's like the world of simplicial sets and then there's the world of spaces and so on, and they're kind of separated from each other. But by building the model structure inside HOD, we can, in the end, express directly like the relationship between the simplicial set, that's just an ordinary combinatorial kind of structure, and the actual shape that it's supposed to represent because they both live in the same system. That's really kind of the main purpose of a lot of this project, I think. All right, so let's look at, this is a kind of overall diagram of the machine that I want to build. So it's going to start with, in the top left, I have this, so category, this ordinary univalent one category that I'm not going to specify at the moment. I'm just going to call it, it's some category of geometric objects. And for example, one geometric object is the n-1 sphere. What I mean by that is in some n-dimensional space, I take all the points that are at unit distance from the origin. So that's the sense in which I'm doing geometry, and it's not, this is not definitely not the synthetic sphere. It's something that actually has points, and they're cut out by polynomial equations in this case. And I can start with one of these geometric objects, and I'm going to apply a sequence of constructions to it. So first, I'm going to apply some construction to turn it into a simplicial set, and then I'm going to take my simplicial set and somehow realize it into just a single set. And all of this stuff on the left side of the diagram is happening with set level objects, but it's still happening within homotopy type theory. It's just the only objects that appear are zero truncated. They're either like individual sets or simplicial sets or whatever these geometric objects are, which are also set based. And that's convenient for this issue of like coherence because, well, in set-based mathematics, there sort of are no coherence issues. And at the very end, I'm going to take my complicated set that I build. Well, a set is a type, okay, just a zero truncated one. And then I'm going to apply some kind of construction called taking the shape of it. And that's going to be this only step that involves producing something that's got higher like automorphisms and things like this in it. The explanation of this diagram is going to be in reverse order. So I'm going to tell you first what are shapes, a little bit what axioms we're using, and then how to build this thing that I called the shape, SH, and then this realization, and at the end, I'll talk about this same operation. Okay, so if we try to do this to our geometric n-1 sphere, we're going to get some rather complicated simplicial set called sing of Sn-1. And then we're going to do this realization thing to it and get some rather complicated set called, well, this. And then we're going to apply this mysterious shape operation. And the fact is that at the end, if you do all these steps to the geometric n-1 sphere, what you get out is the synthetic n-1 sphere, which is correct. That's what you wanted. Of course, you didn't have to go through all this work to build a synthetic n-1 sphere, but you could have put in something more interesting object or some object you didn't already have an analog for, like a unitary group or a Grassmannian or something like this. Okay. Right, so like I said, I'm going to try to work backwards through this diagram to explain what's going on. And I'm going to start with this, what do I mean by a shape? So this is the first axiom that I'm going to add to hot. There's some universe, a subuniverse of types that are called shapes. And I want them to be closed under, well, a few operations. So I want them to be closed under forming sigma types, like indexed by other shapes. And also under finite limits, which basically means identity types, and finite colimits, so pushouts, and the empty type should be a shape. And I'm also going to use the word discrete to talk about shapes. Usually when the shape is a set, so it's h level 0, then I'm going to think of it and just call it discrete because the terminology somehow becomes more convenient. So from these axioms, we can build a lot of actually shapes already. So we can build, I said the empty type, that's a finite colimit. We have the unit type, that's a finite limit. We can go 1 + 1 is 2. We can suspend that by taking a push out to get S1. And now I can take loops on that because I have finite limits, so I can get the natural numbers. And once I have the natural numbers, then I can build sigmas indexed by the natural numbers. And so if I have a sequential colimit, I can also build sequential diagram of shapes. I can also build the colimit, which I can build using sigma over the natural numbers plus another co-equalizer. So in addition to being closed under pushouts, the shapes are also closed under sequential colimits. And those two things are going to come up a lot in the rest of the talk. This terminology of shapes and I guess also discreteness is kind of motivated or influenced by the terminology that's used in cohesion, or maybe also in sort of shape theory generally. Then what I'm talking about would be like the case of something having constant shape. Yeah. But I don't want to assume that my subuniverse S is actually a reflective subcategory. And we'll see an example, which is actually the motivating example, where S is not a reflective subcategory. And that's, I think, so my understanding is this is not how cohesion, it's different from how cohesion works. And this is kind of an important point, I think. One remark about this that is not really relevant to this talk, but it might help sort of contextualize this definition, particularly in relation to the previous talk, actually. If I look at just in the types, so S has some family of types and subuniverse of types, and so among them are some propositions. And which propositions are they? Well, they're going to be closed under the sigma type, and the true proposition will be in S, discrete, I guess we could say. But they're also closed under countable disjunctions because I can build them as sequential colimits of like finite disjunctions, which I can build using finite colimits and stuff like that. Okay, so this is a sort of typical of open propositions in synthetic topology, and this is kind of the origin of the concept for me, at least. But it's sort of interesting to note that in this higher, so this, the S, we should think of as some kind of like higher analog of the open propositions in synthetic topology. It's sort of interesting that the definition kind of got a little bit simpler because we didn't have to put in the natural numbers explicitly, we just got it from other operations. Okay, so I said we don't assume that S is reflective, but still the whole strategy is to take a type and try to reflect it into the subuniverse S. And so there could be some types where we can do this, and I'm going to just introduce some terminology for this. So if I have a map from a type X to some type S, which is a shape, then I just call it a shape map if it's like a universal such map. So for any other shape T, giving a map from S to T is the same as giving a map from X to T. So this is just saying that, again, S is not a reflective subcategory, but there will be some objects that do have a reflection, sort of pointwise defined reflection into the subcategory. And when that reflection exists, I call it the shape of the type. And I write it with SH. So the SH from the previous, from the diagram at the start. And this shape has some good properties because, well, I said my universe of shapes is closed under pushouts and sequential colimits. And so, well, that means that if you try to reflect into such a universe, that reflection will also commute with pushouts and sequential colimits. So if I have a pushout of types that have shapes, then the pushout will have a shape and it will be the pushout of the shapes, and the same for sequential colimits. And maybe one other important thing about this approach, the shape, because it's given by a reflection into a subuniverse, the shape is sort of automatically functorial in a way that I don't have to like construct by hand. So for example, if I have a map from X to Y, and I somehow managed to cook up a shape of X and a shape of Y, I don't have to also cook up a map from the shape of X to the shape of Y because I get it for free because, well, the shape of Y is a shape, and then the universal property of the shape of X gives me the map that completes the square, and that's unique. And so this is automatically, there's no sort of coherence issues here either. And this is the reason for the kind of shape that we saw before. We do everything in sets as long as possible, and then at the end, we apply this kind of reflection into S to avoid any coherence issues. Okay, so let's look at maybe some examples where we could think about this. The first one, which is kind of closest to the axiomatization maybe, is I'm going to be a little bit imprecise here. So in order to tell you what a subuniverse is, I should tell you like what maps it classifies in the model, but I'm just going to tell you what objects are in the universe and as sort of the global sections. The types in this, in one model would be simplicial spaces, like we heard about in simplicial type theory. Then I want to think the shapes are the constant ones. So they are just infinity groupoids that are just viewed as constant in the simplicial direction. Or if we are interpreting a simplicial space as a kind of category, that means that the category is itself an infinity groupoid. And in that case, every type X will have a reflection into the universe of shapes because it's this groupoid reflection that came up yesterday. It just means you invert all the morphisms of the category X, or the simplicial space, I guess. There's another thing that we could do, which might seem kind of stupid here, but we could restrict the shapes to not be all the infinity groupoids, but just the ones that are kind of like countable CW complexes. You can check maybe just externally that countable CW complexes are closed under finite limits and finite colimits and sigma types. And in that case, well, now the subuniverse of shapes is not reflective anymore, right? Because it could be that I take some really big discrete thing, like, I don't know, just some uncountable set, and I cannot reflect it into countable CW complexes. There just isn't going to be a reflection. So that seems maybe sort of useless in this context, but it could be an example to think about why maybe some types won't have shapes. But the actually motivating example for this project was another model, which is the model of condensed mathematics, or condensed anima, or condensed spaces, or infinity groupoids, or whatever we want to call it. So I'm not going to go into a lot of detail about this, but the types here are now these condensed anima in the sense of Schultz or Clausen and various other versions of them. The sets are, well, again, the H level 0, or the zero truncated objects, those are condensed sets. And among the condensed sets are sort of ordinary compact Hausdorff spaces, like the ordinary circle, like the unit circle and the complex numbers. For the shapes, I want to take the constant condensed anima, so they somehow have no existence in this compact Hausdorff direction. They're just sort of constant as sheaves. And for the discrete ones, they're just going to be like the actual sets, which also live as a full subcategory of condensed anima. And in this example, if I take the topological circle S1, it does have a reflection into the subuniverse of shapes, and that turns out to be the infinity groupoid, which I'm writing with this bold S1 because it's like the synthetic circle. This example definitely is not cohesive, because if I take some really bad space like a Cantor set or something, it's not locally contractible, and it's not going to have a reflection into the subuniverse S. And this is really kind of the more motivating example, like why would I want to even allow a subuniverse S that isn't reflective? And this really was inspired by the proof of the Brouwer fixed point theorem in the synthetic stone duality by some people who are in this room. So maybe we'll see that a bit later. So those are the axioms about the shapes. And then here are the rest of the axioms. They concern the interval. So I'm going to ask for a set I that has 2 points around 1, and they're different. That's the first axiom. And the second axiom is that, well, the set I has a linear ordering in such that the least element is 0 and the greatest element. And at the bottom, I'd really like to get rid of this 2' axiom, because I feel like I shouldn't need it, but at the moment, this is I don't know how to work without it. So let's take this axiom 2' for the moment. This is sort of saying that I behaves like the one simplex in simplicial sets. And then the final axiom, which is very important, is that this set I is certainly not like contractible in the hot sense because it has these 2 different points around 1, yeah. But it looks contractible to all the shapes. So the map from I to the terminal type is one of these shape maps. It's the reflection of I into the subuniverse of shapes. So we could say that I is shape contractible, or the shape of I is. So in the previous models, the examples of this would be In the simplicial space model, I could take the actual one simplex. If I invert all the morphisms to one simplex, I get something contractible. I could also take the unit interval in the condensed anima. That's another, I mean, this also has to be proved that somehow if I take the unit interval and reflect it into the subuniverse of spaces, I do get a point. And that's certainly true externally, and I think that probably it can be proved internally also, but I'm not really up to speed on the details of that yet. So the conjecture again was that I can get rid of this axiom 2 prime. That would mean that instead of working in some simplicial setting, I have to work in some cubical setting. It's just a little more complicated than that. Even if I had worked out, honestly, I probably would have presented this because it's a bit more complicated with the cubical version. Okay, so here's our diagram again. We've talked about this last part. I have a way to take a type, maybe this is this dotted arrow, this is like a partially defined reflection, and turn it into a shape, which is the last step in my construction. Okay, so what about, let's look over here on the left. We have this other step. The previous step is to take the realization of a simplicial set. How does this work? Well, this is really a standard thing from ordinary algebraic topology. If I have a kind of interval-like object that has exactly those axioms 2 and 2 prime from before, then it does define a way to take a simplicial set and turn it into, well, wherever my interval object lives. In this case, my interval object just is a set. And so this realization operation will take a simplicial set to a set. So for example, well, the way it's defined is that it takes the n simplex to the subset of I to the n where the points, the coordinates are in the correct order. That's how we think of a simplex as embedded inside a cube. In this condensed example, the unit interval is the actual like physical topological interval. And so if I took a simplicial set, which is just secretly like an ordinary set in every degree, and I apply this realization, I just get like the ordinary topological geometric realization of X that's familiar from ordinary algebraic topology, but now just viewed as a condensed set. So this construction, by definition, takes a simplicial set to a set. It never takes it to a space. That's going to be important. And we define the shape of a simplicial set to be, well, I first try to realize it using this interval. So turn the simplices, which are some kind of abstract shapes, into actual simplices built from the interval I. And then I take the shape of the thing if it exists, and then I call that the shape of my simplicial set K. And then maybe one of the first things that we need to prove is if I start with a simplex that does actually have a contractile shape. So I'm not going to talk about this. So the next question would be, well, I'm handed a simplicial set. How do I know if it has a shape or not, right? We have this sort of partial operation at the end that takes a simplicial, takes a type to its shape. How do I know if I'm in the sort of domain of that operation? And this is where the model structure in simplicial sets is going to start to come into play. So this is just the definition from the constructive version of the Kahn-Quillen model structure of simplicial sets. In the classical version, this condition is automatic because it says that, well, there's some notion of a degenerate n simplex of a simplicial set. And the condition is that they form a decidable subset of the n, like all the n simplices of my simplicial set K. And when they do, I'm going to write n sub nk, and the capital N stands for non-degenerate for that complement. So those are the non-degenerate simplices of K. Well, in classical mathematics, every subset would be decidable. So this is an invisible condition, and so every simplicial set is usually cofibrant. In the constructive version, that's not the case, and so this is some condition that's not trivial. And it's precisely under this condition that we have, well, what is to people do a lot of model category theory, this familiar construction of a simplicial set as a kind of cell complex, right? We can build any simplicial set as the coelement of its skeleta, and then to form the n skeleton from the n-1 skeleton, what do I have to do? I have to attach one simplex for each non-degenerate simplex of K. And so that, in order to make this, even to write this down, I guess maybe, well, no, maybe in order for this to be a push out, I really need K to be cofibrant. And I'm going to refer to this as the cellular presentation of my simplicial set K. So the first thing that we're going to prove about this is that if I have one of these cofibrant simplicial sets, and for each n, the n simplices form a discrete set, so one of these shapes, then I can actually succeed with this, the shape exists, right? So I can always do the realization, and then I want to reflect it into the subcategory of shapes, and this is going to succeed. And basically all the arguments in this area are going to be done by some kind of induction on the cellular presentation. So on the previous slide, we saw that K was a sequential colimit of a bunch of things that are sort of simpler simplicial sets. And then each of the end skeletons is built as a pushout from some other simpler objects as well. And so if we understand sequential colimits and pushouts, then we can try to understand an arbitrary simplicial set K. And so we're just going to try to prove that shapes exist by induction of this structure. And so the interesting bit is we come to the case of a pushout. So, sorry, the pushout that builds the end skeleton from the n-1 skeleton. That's built by attaching a bunch of cells, one for each non-degenerate simplex of K. So that's a pushout in sets because, well, the original pushout was a pushout in simplicial sets. The realization functor by construction preserves colimits with values in sets. So this is a pushout of sets. Now, what we'd like to say is, therefore, the shape takes it to a pushout of types. But there's a small issue, which works out here. But the reason that it works out is that this is not any old pushout of sets. It's a pushout where this left leg is a monomorphism. And pushouts of sets where the left leg is a monomorphism are also pushouts of spaces or pushouts of types in the higher set. So if I build a pushout in types, it's going to be a set automatically. And why is this left leg a monomorphism? Well, because, well, in simplicial sets, the inclusion of the boundary in the simplex certainly is a monomorphism. And the fact about this realization, the hypotheses on the interval, they're exactly what I need to know that this realization functor preserves finite limits or is left exact, which means it also preserves monomorphisms. And so this left leg after realization is still a monomorphism. So when I form this pushout, there's a pushout both in sets and in types. And so if I take its shape, I get a pushout of shapes, which is the thing that I want. And so that's kind of the key point in this, otherwise mechanical. Okay, so this is the more interesting part of the story, I think. There's also a notion of confibrations, or just vibrations of simplicial sets. And we also need a constructively correct definition of those. And so again, I've just sort of looked at the definition in this paper by Gabiner, Settler, and Genoa. A confibration is a map of simplicial sets that has chosen solutions to all the lifting problems against Horn inclusions, right? So it is structured to be a confibration, but it's not a particularly structured kind of structure because we don't ask for any kind of compatibility between these lifts other than the fact that they're given by a function. Okay, so this is like an untruncated definition, an untruncated version of like the naive reading of there are lifts against all Horn inclusions. And now the thing that we would like to prove is that if I have a pullback square in simplicial sets of a confibration, so P from K to L, let's assume this is a confibration. Okay, then P prime will also be because it's a pullback of P. And if all the objects in this diagram are things that I can take the shape of, so they're cofibrant and level-wise discrete, then I want to prove that this pullback square, once I take the shape, I get another pullback square in the shapes, in the subunits of shapes or as types. Right, so in brief, the shape operation should send these homotopy pullback squares to pullbacks of shapes. Right. This is definitely the most technical part of the whole thing. So I'm just going to just very briefly go through this. Well, in order to do this, we're going to introduce some class of maps of types called quasi-fibrations. And this is some kind of version of a notion from classical algebraic topology. It means that the inclusion of like the strict point fibers into the homotopy fiber basically is an equivalence. That's a classical concept that also sort of works here. We're going to reduce to showing that the realization of a confibration is one of these quasi-fibrations. One thing to be aware of is that, well, so actually I don't know. I don't think the quasi-fibrations are stable under pullback. So in topology, it's not true. Here, I'm not sure if it's true, and it doesn't, we're not going to require it. But we do know that confibrations are stable under pullback. So if I started with a confibration, I pull it back, then of course I will get something that realizes to a quasi-fibration also. And then we're going to prove some kind of gluing limits for quasi-fibrations. If I have a push-out square and 3 of the maps are quasi-fibrations and everything's a pullbacks and so on, then the 4th map also is a quasi-fibration. And that's going to rely on some kind of descent property, so some synthetic homotopy theory for push-outs and similarly for sequential pull limits. That allows me to do another kind of induction on the cellular presentation of whatever the target of my vibration is, and reduce to the case of a simplex. But simplices are great because they're they're contractible. And so if I have a fibration over a simplex, then I know by kind of model category theory that it has to be equivalent, like fiber-wise functionally equivalent to some constant vibration. Like, for example, I'll take K prime to be the fiber of K over one of the vertices, and then K is fiber-wise functionally equivalent to like K prime cross delta N. And now if I realize that fiber-wise homotopy equivalence, it gives me a sort of fiber-wise I equivalence, we could say, between the realization of K and the realization of this constant thing. And the constant thing, we know what the fibers are. They're just K prime. And so that's how we can sort of piece this together. So it's really a combination of some kind of synthetic homotopy theory with its descent properties of pushouts and sequential colimits, plus some model category theory style reasoning to know that, well, I can extend an equivalence between two fibrations over a point to the whole simplex. Great. So the summary of this whole section is that I can turn a simplicial set. So under these axioms that I've set up, I can turn a simplicial set that's cofibrant and levelwise discrete into a shape. And this is the construction I've been trying to do. And this last fact about confibrations behaving well under shape tells me that, well, a pullback of the confibration and simplicial sets is getting sent by the shape to a pullback square in my universe of shapes, which is what I need to, for example, prove by some maybe other argument that if I start with some simplicial set that has all of these properties, so it's cofibrant and levelwise discrete, so I can take its shape, and it's also a complex, so the simplicial loop construction will be the right thing, then indeed the shape of the loops on X would be the same as the loops of the shape on X. So that's why all this stuff is really needed in order to, at the end of the day, I want to go back and now build my bot map and realize that I use this fact. Okay. So now I've talked about shapes and this sort of shape construction, this partial reflection. I've talked about how to take a simplicial set and realize it into just a single set, which I can take the shape of. And the last part is to explain just a little bit about what is this mystery category of geometric objects and how am I going to build a simplicial set from one? Well, here's the kind of thing that I would like to do. I'm not going to go into a lot of detail about this. I'd like to take some kind of geometric object. So let me take this example from before. I'll take the n-1 sphere. And so I've written it here. It's the set of points x1 through xn such that the sum of the squares equals 1. Okay, that's the n-1 sphere. And I need to take that specification and somehow turn it into one of these simplicial sets that has all those properties from before. So it had better be cofibrant, levelwise discrete, and it should be a concomplex. And definitely the concomplex part is fine, but the issue is about maybe the cofibrancy and this levelwise discrete. These are kind of new conditions that we're not used to. The traditional answer in homotopy theory would be we use something called the Singh functor. That's just the easiest way to do it. It takes in a topological space and it builds a simplicial set. And the K simplices of the simplicial set Singh of X, they're just all the maps, continuous maps from like the topological K simplex, which is this subset of R to the K into X. And they assemble into a simplicial set. But that's probably not a very good construction in our setting because, well, so being cofibrant, I need to produce cofibrant things in order to take their shape. And it's very unlikely that I can decide degeneracy in this simplicial set Singh of X. So for example, like a one simplex is just like a path in my space X. And the degenerate paths in X are the ones that are constant as functions. So if I'm handed a function from 0, 1 into my space X, and I have to decide whether or not it's constant, that definitely doesn't seem likely to be something I can do constructively. There's also another problem, which is that the real numbers, they might not even be in my universe of shapes. And so it's just way too big a construction if I think my discrete shapes are just like countable CW complex reason. Okay, so this is a problem, but there is a solution to this. And the one that I have in mind is to try to cut down the kind of continuous functions that I allow by quite a lot. So what I want to consider are not all the continuous functions, but only the ones that are semi-algebraic. So they are ones whose graphs can be specified by a formula in the first order theory of the language of a ring. Okay, so and I'm not allowed to use parameters for that. So the formulas themselves, they're just some finite list of symbols, and the symbols are drawn from some finite alphabet. And so a formula is basically a natural number, we could think. And now I'm going to define the k simplices of the Sing of Sn minus 1, not in terms of actual functions, but in terms of the formulas that define the graphs of the functions. So instead of looking for an actual function, continuous function from the topological k-simplex into the topological n minus 1 sphere, I'm going to ask for a formula in k plus n variables that defines the graph of something that's supposed to be a continuous function. And then I have too many formulas because maybe I have multiple formulas that express the same function. And so I need to quotient by this sort of equivalence of formulas that says that, well, two of these formulas are the same if basically they define the same subset of R to the k plus n. Yeah, if t comma x is in the graph of phi, or the graph defined by phi, if only if it's in the graph defined by psi. Okay, well, that might not seem like a huge improvement, but it actually is, because we have this theorem due to Tarski that says that the whole first order theory of real numbers is decidable. So that means that, for example, if I'm given first of all, if I'm given a formula in k plus n variables, I can decide whether or not it really is the graph of the continuous function from the k simplex into the n minus 1 sphere, because I can first write down a formula about phi that says that, for example, for every variable t that belongs to this delta k set, there's a unique x such that phi of tx is holds. And that's some sentence in the language of a real closed field, or sorry, in the, well, yes, or the first order theory of the real numbers. And so by Tarski's theorem, it's decidable. And then I have to check a whole bunch of other properties about phi, like that it's a continuous function. But this also I can define using sort of epsilon delta continuity. And so all of these conditions that describe the formulas I allow, they're actually decidable conditions. And so in the end, this set of k simplices of this simplicial set I'm writing down, it's a decidable subset of the natural numbers, really. So it's also basically also the natural numbers subset. And it's definitely in S. It's a decidable, it's a discrete set now, even though before it might have been built from the real numbers or something. I also need to quotient by this relation that says that, well, two formulas, I want to identify them if they define the same function. This is, again, something that I can decide using Tarski's theorem. And so I have a decidable quotient of n, a sort of subquotient of n that's decidable. Okay, so we built at least a simplicial set, which is level-wise, like the natural numbers or something like it. And it's also now going to be cofibrant. So before I had this problem where if I have a path from the interval into my space x, like from 0 to 1 into x, then I can't decide whether or not it's constant. But here I can also decide whether or not my function, my formula defines a constant function. Because what does it mean to define a constant function? It just means for all t and t prime and x, I guess, phi of tx if and only if phi of t prime x. So that's again another formula to which I can apply Tarski's theorem and therefore decide. And so I really will get out a simplicial set, which has this decidability degeneracy, the n simplices at each level. And so this output of this construction is one of these cofibrant and levelwise discrete simplicial sets. It will be fibrant because, well, geometrically, I can retract a horn onto a simplex in the usual way in homotopy theory. And then the last thing that we would probably like to know is that when I replaced the topological Sing by this new semi-algebraic Sing, I didn't mess up the homotopy type and get something I didn't want. So this is a, well, somewhat classical theorem in, I guess, semi-algebraic geometry. There's a version of it in this book from the 80s. So this is actually, this might appear as though it's kind of a trick that I pulled out, and that is sort of true. But there's also a whole subject of like semi-algebraic geometry that this is just a little piece of that you're seeing. And in semi-algebraic geometry, I can also try to define things like fiber bundles and so on. And then I could try to write down all the constructions that I would need to perform the construction of sort of like Grassmannians and their unitary groups and the sort of sphere bundles and so on. All of that stuff also makes sense semi-algebraically because all of the definitions of unitary groups and all these things, they only depend on polynomial equations. So they're possible to write down in this first order theory, first order language of the real numbers. Okay, so to summarize, this is, I guess, my last slide. Yeah, it turns out that synthetic homotopy theory actually is a lot easier than whatever I just did. So if you can do your problem, if you can solve your problem using synthetic homotopy theory, I highly recommend that. But if you somehow don't have a way to try to solve your problem using synthetic homotopy theory, you could try to do it this other way. It's possible if you give yourself access to a few axioms about the shape and interval, and if you don't mind putting like a rather considerable amount of mathematics into your object theory. And maybe the actual takeaway that I want to sort of get out of this is that there's a sort of mysterious status of what it means to do constructive set-based homotopy theory. And that personally, for me, I don't understand particularly well. And I hope that maybe by building these model categories, such as the constructive Kahn-Quillen model structure internal to homotopy type theory, then, well, because it lets us express directly the relationship between the simplicial set, so an object of this category, and the type that it's supposed to be representing, that might make it a little bit easier to like talk about what's really going on in these model structures, or to compare to structures, or to apply this to producing some things, interesting things in homotopy type theory. All right, so that's the end of my talk. Thank you
all. Question is the existence of an interval I anti-classical?
Yes. If the how do I? Yes, it is. So you mean on this slide? This slide. Yeah. If I had LEM, I could map 0 to. So I know 2, 1 plus 1, that's a shape. And so if I had LEM, I can map 0 to like one of the elements of 2 and everything else to the other. And that would give me a non-constant map from I to a shape. So yes, that's correct. This is anti-classical as far as the like ambient category is concerned. Yep.
So, as you mentioned, these axioms are satisfied in directed type theory. And in that sense, like a lot of these things make sense in directed type theory as well.
That's right.
But there is this one step where you take the I realization and it becomes an actual set. And I suppose that if you work with condensed objects, then you want to think of a set really as a condensed set. So it has a topological structure.
Yeah.
But this step doesn't really feel natural from the directed perspective, because then sets are actual sets. And it feels like an alternative way would just be you take the actual colimits. You have an actual category called simplicial sets, and you can map it into simplicial groupoids and then take the actual colimit.
That's right.
Have you thought about this? And
not yet. So that's definitely something that I should consider. So maybe we can look at this plan again. So what you're suggesting is sort of to go into this forbidden top right region, right? To take a simplicial set, go to simplicial types, and take the colimit to types.
Yes.
Yeah. So the part of the reason I haven't looked at that is that I'm not really sufficiently familiar with the sort of hot-based systems for working with directed and simplicial type theory to do that at a technical level. I would certainly expect that if you had simplicial types or some kind of infinity categories, you could do that construction also, and then you should try to build a comparison map between the two constructions. And then if you can build a comparison map, then just by induction or something, it will be an equivalence.
You mean a comparison map between the lower...
Between going this way, yeah, like I have here, and going over to simplicial types, and then to type, and then this should be the identity.
I mean, but it won't be an equivalence. Like in the directed type theory, you should go the upper way. Like you cannot go...
So if I do it in directed type theory, then the interval is delta 1. So I send a simplicial set to like also a simplicial set. It's kind of it's not quite the identity. A simplicial set is really a bi or tri-simplicial object, depending on your perspective. Does that make sense?
Yes.
Okay.
Maybe I would also like to point out, so a lot of this I actually wrote in my lecture notes. Stable homotopy theory last semester, not in type theory, but it's very similar, so I would be very happy to talk about it.
That would be great. Yes, thank you.
So the question about the problem that the single simplicial set of some space is not covariant. Can you just take the covariant replacement?
You mean at the end? Oops. Can I take the covariant replacement? I think you probably could. One thing that you have to be careful of is, suppose I started with a fiber sequence. Like maybe I start with a fibration and a fiber bundle in geometry, and I take sing of it. I'm going to get a fiber, like a confibration in a fiber sequence in simplicial sets. And then I would like to do a cofiber replacement, but while preserving the fact that it's like a pullback square of a confibration. And that's the part I'm not so sure how to do. Does that make sense? Yeah, I mean, maybe the question could be put in another place. I mean, even earlier, when I said something like, if I have a cofibrant and levelized discrete thing, then it has a shape. But then I could, along the lines of your question, well, why not define the shape for every simplicial set, at least every levelized discrete one, by just doing cofibrant replacement first and then taking shape? And yes, that certainly should be the correct definition. I don't know how that interacts with pullbacks of fibrations and stuff like this, because I don't know if I'm preserving all the properties I need. I think that probably could be made to work. Yeah.
So I'm not sure if that was asked already, but so in the cohesion picture, I would skip the first two steps and directly take the shape of every metric thing.
This one, yeah.
Yeah. And so in your pipeline, yeah. I mean, I assume that there are situations where you can't just take like the inclusion of the geometric category into types and then take the shape, that this doesn't give the right thing. I mean, do you have some example where?
Yeah, so that's definitely true. And that in some models, like for example, in the condensed model, I could have skipped this business of taking sing and then realization.
Yeah.
The reason to do this is that in general, the structure of my interval is it's fairly small. It's just that I have a sort of simplicial interval. But the original geometric object maybe is defined using like polynomials or something like this. And so I don't have any way to take like the sphere defined using polynomials and produce like something that's built out of the interval, because the interval just doesn't support operations like multiplication. In the case of, well, certainly in this condensed anima setting, the interval, it does have multiplication defined on it. And so you can go from a geometric object to a set directly just by sort of taking the real valued points or something of your semi-algebraic set.
So you, in general, you don't know how to prove that the shape of a thing on the top exists, but then you know how to prove that it exists in the, like after the singular realization sets.
Well, so these geometric objects,
yeah,
they are not sets. I mean, this is some other category. Maybe that's.
I mean, by sets you mean Europe, right?
Sorry, they're not just plain types, is what I mean.
Are they not plain types?
There's some other category. That's right. In cohesion, you can kind of get away with treating them as just types, but here they're not. Yeah.
But in the condensed sets, they are.
They have a realization by taking the R points, or real valued points. So then that's a type, and that's another way that should produce the same outcome, in arguably a much more direct way. But we can't do it in general for the reason I said before, that the interval, like if I only have access to an interval that has simplicial operations, I cannot define multiplication, or I cannot interpret multiplication into it.
Okay. One short question, I guess. Did I understand correctly that in principle it should be possible to get all the things you want inside of condensed?
I think so.
Yeah.
Yeah.
Okay.
I would need to understand the work that you did on computing homology a little bit better, but it looks like it should all work out.
Okay. Yeah, cool. Thank you. That's great again.